Hey kids, it's Math here. I'm going to do another couple of thermodynamics problems for you. Got one here set up, and what we're going to do is some more delta G equals delta H minus T delta S. And we're going to do these from standard values that were already provided. So you can see on the screen, we've already got our chemical equations set up. We've already got our standard values for delta H and delta S. These we just pulled out of the appendix in the back of the book. And the question asks us very simply, calculate delta G, and is this reaction going to be spontaneous? So basically, is G going to be negative? If G is negative, this reaction is spontaneous, and it's going to proceed from left to right. So really, this isn't too terribly difficult a problem, very straightforward. In order to do a delta G minus T delta S, we're going to have to know delta H first. So we're going to calculate delta H off of our standards, and this is just going to be a delta H prod minus delta H react. Okay, and so we take our products, and we're going to have negative 1676 kilojoules. Now we multiplied that by this 1 that was out in front of that Al2O3. So it's really 1676. We're going to cancel out the moles because we already used that. And up front, that's going to be minus negative 1128 kilojoules, because also there's a 1 in front of. So if we munch them, crunch them, let Texas Instruments do the work, we're going to find out H is a negative 548 kilojoules. We have an exothermic reaction going on here. Heat is being given off. So that's a good sign towards this probably being spontaneous, depending on our entropy. So with entropy, we're going to do much the same. And we're going to go delta S, and we're going to do products minus reactants again. Delta S prod minus delta S react. No problem. And now everything has a value for delta S. Why would that be? Well, remember, yesterday we explained that the only way something can have a 0 entropy is for it to be a perfect crystal at 0 degrees or 0 Kelvin, not 0 degrees Kelvin. Well, we're going to sneak something in on you here. I usually do that anyway, but this is happening at 25 degrees Celsius. So all of these are going to have a value for delta S. All we have to do is use them. And if that's the case, we're going to take a positive. And notice most of these values are positive for delta S. How come? Well, because delta S is the heat it takes to form something. It takes energy to make something. So 51 plus 2 moles times 24 joules per mole Kelvin minus now our Cr2O3. This one we're going to leave is just 81 joules per Kelvin. Understand, we multiplied it by that 1. We're just doing that in our heads. We're okay with that. Plus 2 moles. That's the coefficient in front of the aluminum here. 2 moles times that 28 joules. Joules per mole Kelvin. Now my moles are going to cancel out very nicely. And Texas Instruments does the work for me again. And I find out that my delta S value is negative 38 joules Kelvin. So now we're starting to get down to the part where we can solve this problem. Now we need to do delta G. Delta G is delta H minus T delta S. Delta H, we calculated up. It's negative 548 kilojoules. okay, minus the temperature, 298. This does have to be in Kelvin, and I did give you 25 degrees going on there. And now we're going to throw in that S. We got to be careful, though. That S is in joules. So now let's change that into kilojoules and turn that into 0.038. And that is a negative 0.038. And if we do this, delta G ends up being indeed very negative, 537 kilojoules. This is spontaneous as written. And so at 25 degrees room temperature, if we put aluminum into this chromium oxide, we're going to get a lot of energy generated. This is going to happen by itself without any outside intervention, and we have a nice spontaneous reaction. We're going to need this one in one of our later videos, so that's why we did it. But this is how you can calculate a G from standard values of S and H. I'm Smath. I hope this video helps you. Look forward to seeing you in the next one.